All set. Okay, great. All right. Hi, everybody. Thanks for coming to my talk on defeating protocol classifying internet filters with Dust. So let's just get into it. I have a lot of slides, so let's go real fast. So hi, I'm Brandon Wiley. I have done a lot of stuff in the past. I made a thing called Freenet in like 1998. My 2001 paper about that is popular in CS. I don't know if you guys have read it, but if not, check it out. It's pretty cool. Kind of started the whole distributed hash table sort of thing, if you guys have read about that. I also wrote Curious Yellow was a superworm design that I designed to destroy the internet. It was just a design. No one's built it because, you know, the internet's still here. But you can read about it in Charles Strauss's book Glass House, in which he uses it as the event that ends humanity, or almost ends humanity, is my superworm being unleashed. So that was cool. I used to work at BitTorrent. For a while, I have fun stories I can say about working at BitTorrent. Let's see, I've worked for the Tor project, which is a big anonymity privacy software on their project OBFS proxy, which obfuscates Tor traffic so that it won't be blocked by people. And then also I have a little chapter in a book by O'Reilly called Peer-to-Peer, Harnessing the Power of a Disruptive Technology. So I know you guys don't care about that. I just want to establish some credibility so that you guys will sit through my talk, because it's kind of long, and it takes a little while to get rolling before we get to the juicy technical stuff. So just bear with me. Hold in there. I got some pictures of cats I need to show you, and then we're going to get to like the real hardcore technical stuff. So I'm a PhD student in information studies in Austin, Texas. So I'm not in CS. I'm in information, which is slightly different. What is information? I don't know. I wrote a whole paper about it. You can read it. I decided that I'm not sure. All right, so talk about some things. I'm going to talk about the internet. What is it? That's like step one before we can talk about it. We've got to figure out what is the internet. I'm going to talk about my project Dust, which is a polymorphic protocol engine. Talk a little bit about how filters work, how protocol classifiers work, and how I can defeat them. If I have time, I have some slides about how to build empirical models of protocol classifiers, and then also some practical applications. And I have bonus slides that we probably won't have time for because I have a lot of slides. So some of this is from my children's book on internet freedom called Free as in Kittens. And some of this is from my PhD dissertation. Let's see how it all mashes together and whether or not it's easy to follow. OK, part one, the internet. The internet, as I'm sure you all are familiar with, is the greatest achievement in human civilization. It's the best thing that we have. It's a way that enables us, no matter where we are in the world, to see pictures of cats, right? So, and that's a sacred right that we need to protect, is the ability to see cute pictures of kittens, and also videos of kittens, and also like posts about kittens and commentary. So really, kind of any kitten-related speech should be protected. So now you can't transmit a cat like this, like a real cat, over the internet. I've tried, it doesn't work. The first thing you need to do is you need to digitize the cat and turn it into pixels, right? So then you get like a cat that looks like this. This is almost ready to be transmitted over the internet. The next step is you need to run it through some kind of like a numerical translation, because as we all know, computers run on ones and zeros, right? So you run it through some color encoding, right? And then you get like a numerical rendition of a kitten. That's ready for internet transmission. Then all we have to do is split it up into packets, because for some reason when they designed the internet, they didn't think that it would need to handle traffic the size of a cat picture. So they said, about 1,400 bytes is probably plenty, right? Who's going to ever send more data than that? So now we got to split up into a whole bunch of like 1,400 byte packets, and then we send it. And then we send it over like an unreliable medium of transmission, right? And then, maybe it arrives on the other side. Maybe it doesn't arrive on the other side. Maybe we have to retransmit it. But eventually we get some packets, and then we kind of paste the packets back together. And then through the magical power of the internet, we have transmitted a pixel-perfect exact copy of the cat that we started with. So there we go. The internet works. Congratulations. OK, so now we have established some cat-based terminology for talking about the internet. Like I said, it takes a while to get going, but we're going to get into the juicy stuff. OK, so what's the problem? The internet allows us to transmit cats. What's the problem? Well, the problem is robots. We don't know why robots hate cats. when asked, they said that they were just programmed that way. And so the problem is that robots, when they see cats, they determine, is this a cat, yes or no? It's a binary classifier, right? There's only two options because they're robots. They don't have a wide gradient of opinions about cats. They say, is it a cat or not? If it is a cat, then they replace all of the pictures of cats with pictures of sad pandas. And nobody likes that. There's no joy there. And if it's not a cat, then they don't care, right? So they just go ahead and pass it through. Nothing happens, totally unmodified, right? OK, so the question is, since we want to support the viewing of cats on the internet, how do we fool robots? How do we make it so that we're transmitting cats, but they do not see cats? They see something else, and then they don't care, and they let it through, right? So obviously, what we need to do is we need to package up pictures of cats so that they look like they're not pictures of cats, right? Right? So then that's it. So we have some kind of a transformation that's a reversible transformation. We still need to get the cat out of the banana suit afterwards. Otherwise, that would be catastrophic. Thanks, guys. Right. OK. So here's the secret code to my kitten slides. So kittens represent free speech. Sad pandas are censorship of the internet. Robots are filtering hardware, which is manufactured mainly by American manufacturers in California and sold all over the world to governments that oppress their people by not allowing them to get news about the country that they live in, not allow them to read about election reform and election fraud monitoring, stuff like that. And bananas are messages that get past the filters, and the banana cat is free speech that has been encoded to get past the filter. So this is serious stuff, I guess you could say. It's free speech and the ability for civilization to function. OK, so right. So then let's talk about dust. So the point of dust, as established by my terminology here, is dust makes cats into bananas in order to fool robots to avoid sad pandas. Right? Everybody following with the cat metaphors? OK. OK, so there's some other approaches to doing this same sort of stuff, right? So there's obfuscation. Obfuscation is where you take your traffic and you make it look like who knows what, just like nothing, just like random noise, right? And so OpFS proxy that I worked on for Tor is along these lines. So all of this obfuscated traffic basically looks the same. It all looks like kind of random noise. The problem with that approach is that a filter can say, hey, you know what? Things that I don't know what they are, let's go ahead and block those things. Let's only let through things that I know what they are. So that's kind of like the blacklist versus whitelist approach to filtering. So on the whitelist side, there's these mimicking protocols that say, OK, well, let's make all of our traffic look like, I don't know, HTTP. HTTP is OK, right? HTTP will get through. Nobody's going to block HTTP. And that's kind of an interesting approach. There's some downsides there. People used to say that about HTTPS. They said, no one will ever block SSL because, banking, online banking, right? Well, it turns out that some countries don't really have a lot of online banking, and so they just didn't care, and they totally blocked all HTTPS. There was a thing that happened recently where they blocked all protocols except for HTTP, and you could only have a 60-second connection, and they would automatically reset it. So you couldn't even really proxy stuff over HTTP. You had to proxy it over a bunch of short-lived HTTP connections. The most promising research in this area, other than my own, which I think is pretty good, is format transforming encryption, which is by some guys from Portland State. And what their stuff is you give them a formal grammar for the protocol, and then it will encode your traffic to conform to that grammar. So for something like HTTP, when you have a grammar, then that works. However, this means that you have to have a grammar for whatever traffic you want your traffic to look like, right? So there's some things that maybe we don't know so well. Like IRC, for instance, is a protocol that who knows what it is. You just have to kind of look at some IRC traffic and figure out how to implement it. OK, so my project, Dust, it's not a protocol. It's not a single protocol. It's an engine for generating protocols. So I can generate just a vast variety of protocols. So it's not a thing where you can see my protocol and say, OK, how do I block this new protocol? Like with OpFS proxy, it's new protocol. People have caught up with it somewhat and are now blocking it. With Dust, you have to say, what is the space of protocols that could be generated here, and how do I detect that the traffic I'm seeing is within that space? And I use a statistical model. Every packet is encoded individually. Some people think that this is not a good approach, that you should encode the whole transmission. But I would say look at the empirical data, and you'll see that the hardware is per packet filtering. And also, you don't need a grammar for my stuff. You can just sample traffic. Show me the traffic that gets blocked. Show me the traffic that gets past the filter. I will make your traffic look like what gets past the filter, right? For just any filter. Doesn't care what the filter is. Just show me the traffic. And right, so what I do is I model the filters. I say, how does the filter work, and how do we get past the filter? Whereas other approaches are kind of saying, let's find a protocol that'll get through and try to figure out how to make stuff look like that specific protocol. So I'm aiming for this realistic threat model. Like I want to defeat not what people are writing about in CS papers on filtering and blocking. I want to defeat the actual filtering hardware that is actually deployed in the world in the way that it's currently configured and is being used to filter the internet. Also, some of these protocols use like shared secrets, and that's just not. It's very weak. So everything I do uses public key cryptography. But everybody's kind of moving towards that. But it's a little bit of a differentiator. So my general point of view is it's a hard problem to say, let's take a global omniscient adversary and try to make unobservable communication. And that's, I think, what people in CS are generally working towards. So basically, someone will write this paper. They'll say, OK, I've made totally unobservable communication. No one can ever observe it. And they publish it. Congratulations to them. And then someone else comes out with a paper where they say, hey, I figured out how to observe that unobservable traffic. And then they publish. Congratulations to them. But we're not really moving forward, right? Like we're just saying possible, impossible, possible, impossible. So a much easier problem is let's take a local adversary that we know how they're classifying traffic, and let's attempt to get traffic past that adversary. This is would generally be not a very publishable result. It's too empirical. But these are the real adversaries, right? So that's what I'm trying to do. And so there's this paper in particular called The Parrot is Dead, which is a great paper. It got Best Paper Award at Oakland Security 2013. Highly recommend that you read it if you're interested in this area. And what they basically say, their paper is called Observing Unobservable Communication. And what they say is, we basically think that as CS professors and PhD students, that we can differentiate all of this traffic that people are trying to hide in the lab. We can do this analysis offline, and we can distinguish it very well. And in fact, they cite my paper as an example of what not to do. So thank you to them, because a citation is a citation. They say, like Brandon's dust protocol, a per packet model will never work. My response there is the hardware is doing a per packet analysis. So a per packet model will totally work if you could take these CS professors and grad students and put them in a box and replicate them and sell them to all of the countries of the world, then I would have a real problem. But luckily, everybody's using 10-year-old hardware, and I know how it works, and I can defeat it. So that's kind of my point: is let's try to solve an easier, more realistic problem. Oops, my slides froze. There we go. Yeah. OK. So the general idea behind Dust is choose a set of properties that traffic has, whatever set of properties is being looked for. So packet length would be an example of a property of traffic. Define how it's classified. For instance, maybe you classify packet length. Maybe there's a bad packet length. BitTorrent chunks up its traffic into packets. And so you can say, based on packet length analysis, this is BitTorrent traffic, right? So you have a bad packet length, a good packet lengths, and that's your classification rules. And then Dust will generate an encoding that will randomize the given properties so that they don't leak any information about the content. But instead of randomizing them purely random, it randomizes them according to a probability distribution to match whatever traffic you're trying to mimic. So this turns it around. Now it's a hard problem for adversaries. The adversaries have to determine, is this traffic that I'm looking at one of the many different possible encodings that Dust can generate, right? Is this traffic that I wanted to block, but it's been encoded in one of these different ways? And I think that's a hard problem. I think that is probably an incomputable problem. I don't have a proof, but if anybody wants to work on a proof that censorship is incomputable, let's write a paper, and we could publish that. All right, so moving on at a rapid pace. Let me get some water. OK, protocol classifiers and how to defeat them. Back to the cats and the robots. OK, so So this is one of the ways that protocol classification works, is you look at just the packet lengths. You look at just the packet lengths, and you say, OK, these are the packet lengths that identify this kind of traffic. Now, sometimes people are skeptical when I tell them this, that this would be an effective means of looking at the type of traffic, because you're not looking at the content at all. Like, the packet lengths are something that's on the network level, right? Or so people say. Well, it turns out that applications actually do chunk up their data in these certain size packets, and it's distinguishable. So I'm going to show you some examples. OK, this is the distribution of packet lengths of HTTP packets. So way there on that end, that is not like the end of the graph. That's actually a spike, a giant spike in packets. Does anybody know why? No? No networking, guys? Yeah? Right? Right? But the reason that everything is at the maximal transition unit size is because of the Nagel algorithm, which says, hey, if you send a bunch of small packets, I'm going to just go ahead and not send them. I'm going to buffer them, put them in one maximum size packet, and just send that, right? So you'll see this for like a lot of protocols that send tiny packets, right? So HTTP is one of those. So that's what HTTP packets look like. Here is SSL, specifically HTTPS. So they disable the Nagel algorithm with the TCP no delay flag, and that means that there's no Nagel, which means you don't see this spike. You see this kind of other weird distribution. You still have a pretty big kind of spike towards the maximum packet length, because you're going to find that generally in protocols that send a lot of data, they're going to try to max out their size when they can, because it's more efficient. And then you have kind of this little spike over here. All right, now here's the deal. I'm going to now show you some traffic, and we're going to vote on which it is, and we're going to determine whether or not we can determine by packet lengths what protocol something is. OK, are you guys ready? OK, raise your hand if you think this is HTTP. OK, raise your hand if you think this is HTTPS. OK, congratulations. You are a Cylon. I fooled you. That was actually Dust, the polymorphic protocol engine. Yeah, it was shaping the traffic to have the packet lengths of HTTPS. So this is actually a blog post that is over my own proprietary protocol that's basically just like JSON over a socket. Yeah, so now we determine not only can you tell the difference by packet length, but also I could fool you by giving you mimic packet lengths. So the moral of the story is that Dust removes packet length information, and it replaces it with a target distribution. This is going to be the overall theme of this section. I take all the information out, replace it with target distribution. OK, next thing. So another way is you can say, OK, yes? Oh, right. So in that case, I disabled Nagel. And that's actually a good point there, is that if you don't disable Nagel, you don't have full control over your packet lengths. But if you leave Nagel on, your stuff's going to just look like Nagelified traffic anyway. So it's only really, it only makes sense to do this packet length emulation stuff for emulating protocols that don't have Nagel enabled. That's a good question. OK, so you can look at the content, and you can count the probability of different sorts of bytes. Now, this actually makes sense. Like, this could be in a picture of a kitten. This could be like the color of the kitten's fur maybe is 6. So you see a lot of those pixels, and you think that must be a kitten. People actually tried to do this a long time ago, like in the 90s, 2000s. They tried to filter out nude images by looking for skin tones. They would just look for skin tone pixels. And they found two things. One, pictures of unfinished wood furniture looked like nude humans. And second, nude humans who were black and white pictures got past the filter. So it didn't work very well. Right, so this is, so looking at content. So I have some things here. So here is, yeah?
China still does this, which leaves people unable to find pictures of pigs.
There you go, pictures of pigs. Awesome, little problem. Yeah, that's cool. So here's a content analysis. This is analysis of English dictionary. And so the big spike is new lines, because I didn't process out the new lines. And then there's another spike that's spaces, because some words actually have spaces in them. There's a little bump of capital letters, and then a big bump of lowercase letters. Okay? So that's what English language text looks like if you do like a frequency analysis of it. Okay? Now here, oh, I'm sorry, here, and now I've circled it for you. Here are the lowercase English letters. Okay, here is HTTP. So notice that there's still a spike in lowercase English letters. I think people have this idea that like when we wrap stuff in protocols, that it destroys the lower level information. But HTTP has a lot of English style stuff in it, right? Like all of the tags, and of course all of the content of the pages. So this is just straight HTTP. It mixes images and CSS and HTML all together. I don't differentiate. But you can still tell that this is, whatever protocol it is, you can tell that it's got English language text in it because it's got this spike right around the English letters, right? Okay, and check this out. This is HTTPS. It still has a spike, right? Even though it's encrypted. And the reason is because the handshake before you get encrypted in HTTPS is not encrypted. You have an unencrypted handshake. And that has the certificate information. The certificate information has English names in it, right? It has like the names of the company and the name of the certificate authority and stuff like that. So even though this is encrypted, you can still tell that this is English traffic, right? And that's how they get you with HTTPS. That's how they filter HTTPS, is they look at that unencrypted handshake, and then they can tell that it's HTTPS, and they can block it. And so Tor, for instance, pretends to be HTTPS, and they're able to find, you know, kind of differences. Like at one point, they were using a different certificate authority than a lot of people. They switched to the same certificate authority that Apache uses, and then that helped them for a while. So anyway, right, so what I do is I just remove the statistical content. So whatever traffic you give me, I'm going to encode it. I use what's called a reverse Huffman encoding. So Huffman encoding is a way that you can take something with a probability distribution and you can compress it. And compressed information, of course, is all evenly distributed, right? So it's like equally random. So I use reverse Huffman encoding. I take the encrypted information, which is totally random, and then I reverse Huffman encode it to make it fit whatever distribution. So I can make, I can make it look like just all English text. I can make it look like HTML, HTTPS, whatever. Now again, this is statistical. This is purely statistical level that I'm doing this. So if you were to actually look at the traffic, you would say, this is just like if I did like English text, right? You'd be like, this is just a gibberish of lowercase letters. This doesn't mean anything. And the reason I do that is because, again, the hardware is looking at these statistical properties. In particular, what some of the hardware looks at is it looks for random looking connections, right? Which it says, in particular, if this is an unclassified traffic, I don't know what it is. And if it's random looking, then that means that it's probably somebody trying to hide something and get it past the filter. So I'm going to go ahead and just block all of that, right? So the key is not to emulate any particular thing. It's to lower the amount of randomness until it no longer looks random looking to the filter. So that's all I'm trying to do. So it's very, very easy as compared to what like the FTE guys are doing. Now the FTE guys have, with the grammars, they have the advantage they can get past a proxy, which actually like parses all of the headers and everything and like validates what kind of content you're doing. That's not my target. My target is deep packet inspection filtering hardware. And so they use much simpler mechanisms. In fact, the most popular, most widely used algorithm for filtering, you're going to not even believe me because it sounds so dumb, is they look for these static byte strings in the first packet, sometimes in the first few bytes. They say, does it say 608.787 at this point in the packet? Or maybe somewhere in the packet, they can use regular expressions. That's the most popular thing because it's fast, because it's easy. Think about it. If you're making filtering hardware and you need to filter all of the internet of a country, you want to look at as little traffic as possible before you decide how to classify it. So if you can look at the first packet and make your decision and then just pass everything else through, you're going to be able to scale up a lot bigger to the amount of traffic that you can do. So that's what they do. So I remove those sequences of bytes because I'm already doing that because I'm encoding it with this reverse Huffman encoding. Now, one thing that I don't yet do that I need to do in the next version is producing these sequences of bytes. So like, for instance, the way they look at HTTP is the request, does it either start with POST or GET space, right? Get and post are the first 4 bytes of HTTP requests. There's head and there's a few other things, but you get the idea. So I need to be able to produce those first 4 bytes that are the right bytes in order to pretend to be, for instance, HTTP. And I have done tests, and this totally works. I can make, for certain hardware, I can make any traffic look like open VPN traffic by just setting just 3 bytes. There are 3 bytes in the first packet that have to be certain values, and then that's all it looks at. So, So I'm not making this up. This really works on actual like production hardware that's being used to filter countries right now. Okay, so this is all, yes, question?
So you mentioned that this sort of thing has to be decrypted against the other side. Does anyone have any idea what's going on? Like when they receive this thing that looks like random HTTP gibberish.
Right, yeah, so that's the thing about my approach is that it requires like client and server. So like you need to be running a server that knows what specific protocol parameters you're using. And so, and I have slides about my whole cryptographic protocol that I'm going to do if people care, but that's part of it. So my cryptographic protocol relies on, some people think this is cheating, but I think this is the way to go. There's an offline, like out-of-band components. So if you think about it, you need to have the IP address and the port of who you're going to connect to before you connect to them anyway. So I just require that while you're getting that, you also get their public key, and you get the set of parameters that you're using to communicate. And I have this nice little invite file that I generate, which I actually do all of the randomization of length and the reverse Huffman encoding. So you can't tell if a file is an invite file, because any file could be an invite file, right? So anyway, so yeah, you get this invite file, and then it allows you to connect, and it knows how to connect. So yeah, okay. So sometimes, yeah, go ahead. Right. So that's a clever trick. So it's a self-delimiting encoding. So basically, with the reverse Huffman encoding, if you use every symbol once, then I know what the symbol set that you used is. So I keep encoding it until I get an encoding which has used every symbol. And then when I get the file, I say, so for instance, binary, 0 and 1. If I see a file that has only 0 and 1, I say, this is binary, and then I decode it that way. If I see a file that has, 0 through 9, A through F, I say, this is hexadecimal, I decode it that way. But for the full range of different combinations of ASCII characters. Does that make sense? I know that's kind of esoteric. Yeah? Oh, no. I mean, it's like a random looking binary blob. It's of different priority shapes. I have thought about that sort of stuff. The problem with steganography is that for the most part, you can detect steganography. And that's why I say that what I'm doing is not steganography. There's no cover traffic. Like I'm just encoding the traffic in a way. That's why the other guys call their stuff format transforming encryption, because their thing is like a form of encipherment. It's not really a steganographic approach. But I have put some thought into that. Yeah.
I didn't quite get what you said earlier, but basically, my question is, how do you make sure the invite is not blocked, and why can't you just do that for everything else?
Right. Well, so for the invite, you only need to have a low bandwidth channel, right? So if there's any channel, like you could send someone a note. You could send somebody an email. It's a low bandwidth channel that lets you bootstrap into a high bandwidth communication with the outside world, right? It's, I think in general, if you're going to give somebody a tool, you need some channel that you can get to them. You need to give them the binary for the tool, right? You need to give them the IP address. So there needs to be some kind of low bit rate channel to people to get them bootstrap on a network generally. And so I go ahead and have that requirement. But once you get the invite file, then you can just do arbitrary communication like outside of the network. So it's kind of like a bootstrap is the way I look at it. Okay, so I'll have a couple more slides, and I have my bonus slides that will hopefully I can use if anybody has questions. So sometimes people ask me like, okay, so what are you going to actually do with this? Somebody asked me today why I was creating a general purpose tool to defeat network management when people have legitimate reasons to manage their networks. And so my point there is like, yes, these are general purpose techniques. You can read my papers, and you can write your own things that will get past any kind of filters. You can get past your filters at work to do things you're not supposed to be doing at work. But that's not my goal. My goal is internet censorship. And so I'm trying to build this thing on top of Dust called Operator, which is basically a set of services that run over Dust. And part of it is a database where, based on what country you are and what kind of filtering exists in your country, it will get a set of settings automatically. So you don't have to download those settings. You have like a little cache database of them. And so, and then it will determine what kind of encoding will get you through that network, and then it'll find a proxy for you that you can access from where you are. And it'll do everything automatically, and then you just have that service. It's as if that service isn't blocked. And then these models are models that I've developed I do empirical testing. When I get access to hardware, I have a test framework where I generate models based on the actual hardware. When hardware is not available, I can use sample traffic. And because these are Bayesian statistical models, if all I have is an anecdotal report of what's being blocked in a country, I can generate a model based on that report, right? That's not as accurate as if I actually have the hardware, but it's better than just not using anything and just being blocked, right? Like it'll get through some percentage of the time. And then as we get more data, then we can refine the model until we have a perfect model, or as perfect as is empirically derivable. So, right, and then you have this database, and then you can connect to these services. So one of the services that so this is my picture of happy cats, right? So we take all of the cats in the world, encode them as bananas, get them past the robots, and then everyone can have love and peace because they can be reunited with their cats. So, that's my vision. It's a utopian vision. So like one of the specific tools I'm working on is I'm working on an RSS News Reader because news, in particular blogs, are the most filtered content on the internet. And so I just want to it's a very simple tool. It's just like Google Reader, but it's a desktop app. It uses Dust so that it gets to your news feeds. I download them for you, and then I encode them, and then I send them to you, right? And so this is, people always ask me, like, could terrorists use your stuff? And I say, well, if they want to read the news, they could. They say, people use it for illegal activities. I'm like, well, criminals can use it to read the news, but that's all they can do, right? Because that's all I'm actually building, that's all I'm actually shipping. And I have ideas for other things like email and things like that, but I wanted to kind of start with like the most kind of a use case that I think we can all agree is something that is good for the world, is the ability for people to read news. So I think that's, fairly unobjectionable. I don't know. So anyway, that's what I'm actually working on in terms of actual applications. Cool, and then I have, my link got cut off. I have a paper, and then I have all my stuff. It's open source. It's all on GitHub. And I have a bunch of bonus slides. So I'll just take questions. And then if anybody has any questions on my bonus slides, I can use that slide. What's up?
So your protocol isn't designed to remain undefeated against an adversary who knows that where it's running dust. Like if I as a sensor knew that their dust was becoming a problem, try to figure it out, sort of block it?
No. So something that's just obscurity won't work very long. And that's, I think, what people have tried in the past is they say, well, let's just switch to a new protocol that doesn't look like the old protocol. And that works for a while, but if you have an adversary that is actually paying attention and actually cares, empirically what we found is that they catch up pretty quickly, and then you have to make a new protocol. And it's like a cat and mouse, and it takes a while, and it's a lot of developer resources. So Dust is not a protocol. Dust is a protocol engine that can make a wide variety of protocols. So knowing that someone's running Dust is not sufficient. Now, of course, if you know that someone is running, if you know a specific IP is running Dust, you can just block that IP. And that's on the client side and the server side, right? So that is a problem. And so we do want to avoid detection just because IPs are not super cheap to get. Server-side IPs are not so bad, but client-side IPs, once you're blocked, you're blocked. But yeah, once you realize that Dust is a problem, now the question is, okay, well, Dust is modeling our filters. Let's change our filters, right, would be one thing you could try. But then, I can update Dust. It's cheaper to update Dust because it's just new settings than it is to come up with a whole new protocol, right? So the question is, can I be faster in pushing updates than the sensors can be in figuring out what's going on and updating their filtering settings? And it really comes down to a question of who has a better model. Do I have a better model of their filter, or do they have a better model of my model of their filter? It's a little confusing. Now, so people have asked me, so in the iterative game of the filtering software and the Dust software, and we're iterating to try to defeat each other, what's the end game there? Now, I feel that if you really understand information theory, that my opinion there is that the circumvention software is going to win because it's easier to come up with a new encoding than it is to find a set of filtering settings that perfectly differentiate traffic into two categories with all the traffic you want to let through in one category and all the traffic you want to block in the other category. In particular, I think that it is difficult, it's a hard problem to determine if some traffic that you're looking at is actually encoded traffic that you wanted to block with an unknown encoding, right? I think that that is a hard problem. The thing you got to understand is this is not like a laboratory setting where they're looking at some dust traffic and then some like legitimate traffic and then saying, okay, I can see the differences. This is all of the nation's traffic, and you have to find which signals in there are encoded signals, right? So I have the whole mix of all of the traffic to hide in. And in particular, I feel like there's not like one solution for what protocol you should be. You should make a probability model, basically, of all the traffic coming out of the country, and then distribute your encodings over that entire probability model. Like, a lot of people go straight for HTTP, straight for HTTPS. And that's the wrong way to go, because that's what the filters have the most visibility into. That's what they're spending their resources differentiating. You should get, like NTP, NNTP, FTP, Oracle, like the MySQL wired protocol. I spent some time making models of just the, when you go to the administrative interface, the web interface of some of these filters to like administrate the filter, I built a model of just that traffic so that if the filters went ahead and blocked that traffic, they might accidentally block their own access. Now, of course, if you pay attention, you won't, because it's like different interfaces. But just to mess with people, I thought I would just go ahead and do that. There's also, they have a proprietary protocol for sending like statistical data out of the filter to like another computer that like aggregates it and makes charts and stuff, and that's like a UDP-based protocol. So I built like a model for that. So again, you might accidentally cut off your own access. So yeah, did that answer your question? I kind of went off too. Yeah, okay, yeah. Well, yeah, so China specific, yeah. Right. So I don't specifically think of China as an adversary that I am going up against, because they have the best filtering in the world, much respect, just really good. They have multiple PhDs. They publish papers on their filtering technology. Like I consider my statistical, like Bayesian modeling based approach to be like pretty far ahead of the other approaches in circumvention. Their filtering is like equally far ahead. Like they're using Bayesian statistical modeling to build filters, and no one else is doing that, right? And so I feel like there's hundreds of other countries that are buying off-the-shelf hardware, and it's a much easier problem. And I'm gonna just free the internet of all the other countries except for China. That's kind of in the circumvention space, I think, what everybody focuses on. That makes sense, but I think that they're leaving everybody else behind while they're battling this really hard fight with the Chinese firewall. So no, and then the other reason no is that I don't have proxies in all of the different countries. So that's something that I'm working on. So far I've had access to the hardware, and so that's been really informative. But having proxies where I can send traffic through the filters of different countries would also be super useful to test the stuff in the field. But I just don't have that access right now. Yeah.
So one thing I see is, like, speaking of your proxies, is everything needs to go through them, right? And like it seems like it's really easy for adversaries to get the list of publicly available proxy IPs and just block them all.
That is a smart observation, and that is actually what people do to Tor. Tor has public proxies, and in some countries they're all blocked. But my project doesn't have public proxies, so that's a difference in the way that we're doing it. So I'm not providing a public service. What I'm doing is I'm working. My goal is to partner with NGOs in different countries and say, hey, I have set up a server just for you. It's your own IP, and give this to the people, the community that you serve in that country that need internet, right? And so if their IP gets blocked, none of my other IPs for other countries get blocked. Only that country loses access. And also I know who's leaking my IP addresses, right? Like I have specific point of contact. I say, hey, you got to be more careful because your IPs are getting blocked. That's a big problem. When you're doing a public service, updating everybody with the new IPs is just as hard of a problem as a lot of the other problems people are trying to do. Especially China's really awesome with this. Again, they block Tor so awesomely. They basically enumerate all of the Tor nodes. They go in and they just continually are updating their list of Tor nodes, even the non-public ones, and then they're just all blocked. Okay, let's see. Way up in the back. Oh yeah, so where am I on the roadmap? So the operator stuff, where I'm building the database, and then actually building services, that's future stuff. So the stuff that I've done so far is I've done Dust version 1, which was a pure obfuscation, kind of like obfs proxy or other stuff that was out there. And then I've rewritten. I got Dust version 2, which does all the shaping stuff. I have recently been kind of packaging it into like a reusable library, and then also I have all of my tools that I use for investigating and building the models, and I've split those off so other people can use those. And that's my next step. And so that's kind of a, it's like in terms of building tools, that's like a funding limited step. Like I'm trying to get funding to build those tools or to build the services. In terms of the research, I'm partnering with nonprofits that work in countries to be able to do the research and build the models. So I'm currently building the models, I guess, is where I am on the roadmap. I'll get to you in a minute, but I got to get some other people to ask a question. Yeah. Uh-huh. Can you tell me what product? Uh-huh.
And over like hundreds of packets, and just like build models. And we had some prototypes that would even do something like SVN on a bunch of attributes.
Sweet.
So, I mean, what I'm saying is, it's just a matter of time when these guys will build far more sophisticated systems. So,
Yes.
Shaping traffic into a certain, to mimic like traffic as a certain thing, right? And how far do you think, or how, I mean, doing that, but there will be a point when you will also sort of face that same wall.
Yes.
What is your strategy? I mean, you said something about encoding the sort of easier.
Mm-hmm.
But is that the only thing you're going off of, or do you have more? Because silicon is going to get cheaper and cheaper, and countries will start buying these more sophisticated products. I mean, right now in Pakistan, they're blocking library and Skype.
Yeah.
I mean, so is this going to get?
Yeah. So yeah, that's a very interesting question, and I would love to talk to you about your product and find out everything about it so that I can make a model for it. So there's two different things I'd like to say here. One is, so the way that the product cycle works in this industry is everybody bought all of their packet filtering stuff like 10 years ago from one very popular vendor, and they don't update it. So it's actually a very slow update cycle for countries to replace their entire infrastructure with these more advanced infrastructures. Yeah. No, Cisco is actually not that strong in this space, surprisingly. I'd be happy to tell you guys all about the vendors when I'm not being recorded. Just I don't want to make them mad because I like them. I like them. They're cool. We're just on different sides of the same process. We're both looking at the same data, right? We're looking at the traffic. So no animosity. So anyway, so I have a lot of lead time with everybody except obviously China. That they build all their own stuff and their stuff is awesome. But most people are buying off-the-shelf stuff. It's old. So from a practical standpoint, I stand by that the things that I'm looking at now are like the most important things to look at, the most important attacks. And while the CS literature has gone off into these like super advanced attacks and defenses, they're not actually building tools that work. And so I'm going to focus on that. Now, in terms of when people do, and they will definitely eventually update to these like more advanced, much better techniques. And in fact, I've looked at some not as popular but much more advanced hardware. And it, it's a lot better. If people just update their stuff, they'd have a lot more effective filtering. So yeah, it comes down to I think that it's easier to write an encoder than it is to write a filter. But there's not going to be any way to prove that until we actually get to that time. So if I could get access to some of this really advanced machine learning based hardware, we could do some iterations and we could find out the answer. So if anybody wants to dance, then let's do that. That sounds like a fun time for everybody. But yeah, I can't really prove it until we get to that point. That's my intuition. Is that one side is either the other side. And that's from my study of information theory that I came to that conclusion, and that's what led me kind of in this direction. Was I had this inside information theory, and then I said, hey, this is actionable. We can use this to actually hide information. But yeah, it's an interesting question. Who else? Yeah, up in the back. Well, so that's not my nodes for my system because my system is not deployed. But for Tor, that definitely they have had everything you can imagine. One of my favorite things that that somebody does to Tor is whenever you make an SSL connection out of the country, because Tor masks itself as SSL. When you make an SSL connection out, this one particular country will make their own SSL connection to that same port and then ask it if it's a Tor node. And if it says yes, then they'll blacklist it. Super cool. Super cool. You got to respect that. And Tor has also been under, they have de-anonymized users. I was actually at the PETS conference, and somebody was talking about how they had broken the Tor network by DDoSing it in order to de-anonymize some actual users. And everybody was all like, what are the ethical implications of this? Like, these are actual people. And they, being from CS, they're like, oh, we didn't think about that. So, but they published a paper at PETS where it was exactly that. It was a DDoS on Tor. So, you know, I think that for my system design, the thing that's going to help me there is that it's not public. Like, I'm going to give everybody, all participating organizations, their own servers. So it's at least limited in that you could DDoS one of the servers, and that would certainly take it down. If I get DDoS, I'm just going to take it down and then just wait and then bring it back up. That's my approach. Yeah?
I have a question about how you analyze the traffic. So it sounds like you said mostly it was the traffic.
No, so actually what I mainly do, and I have some slides on this. Right, yeah, so what I actually do is I built this set of tools, and I have this tool, replay tool, is my first tool. So what it does is it takes captured traffic, and then it will mask it and try different variations to figure out what byte string that they're using to identify the traffic, right? And so that's just a straight up just a captured traffic, and that's like the real simple one. And so actually, in this case, I had the hardware, and I was actually experimenting with variation of traffic through the hardware and seeing how it classified it. And then I have this other tool, Shaper, that you send it some stuff you know it's going to block, and it blocks, and you say, good. You send some stuff you know it's going to pass, and it passes it, and you say, OK, good. I have the delimiter of the filtering. And then you send it some crazy stuff, and then you see what it does with it, and then you kind of map out the shape. And so for that, I actually build a model, and then I give it the model to Dust, and then Dust generates traffic that conforms to that model. And then I tweak the model, and I kind of move the probability curves around, and then I see kind of where the fall off is in the classification. And so that's my research to date has been based on empirical experiences with the hardware. But the model building tool just takes traffic samples. And that's how I build my models, is I just generate some HTTP traffic, and then I build a model. And then I replay it through the hardware, right? So, so similarly, if you can send me traffic samples, either of traffic going into or coming out of a country, and you can tell me you know, what's getting through and what's being blocked, then I can build a model based on that traffic.
Yeah, that's what I was wondering, if you're actually getting that real information on the other side of the firewall.
Right. So I don't have that now. I'm partnering with nonprofits in different countries to basically set up clients in those countries, and then we have a server, and then I'm writing a nice little things. I have this other tool, blocking test. So what blocking test? I wrote it for Tor like a couple of summers ago, and they're not using it. It didn't really work out. So what blocking test does is it generates automatic traffic. So like for web traffic, for instance, it uses Selenium, which is a thing that actually lets you drive a real web browser and like go to sites and does the full like all the CSS and all the HTML, and you can click on buttons and everything. Nice realistic traffic profile. And then I do full packet capture, and then I build models based on that. And so so I'm working on right now making an automated tool where basically like you just have a command line tool. It runs on Linux. You run it. It runs all the tests. It runs like trace routes and stuff to map the structure of your network to see if there's choke points where everybody's filtering. And then it does tests all the different ports and the protocols and tests different traffic variations and stuff, and just makes a file, and then you can email it back to me. And so if anybody knows anybody in filtered countries, I would be happy to send this to you when I get it done, and you can run it, and we can build a model. Yeah? Oh, I don't know. So my experience with filtering equipment has actually been that it's mainly online. They do a decision usually on the first packet, maybe up to like 14 packets. Now, if you're finding anomalous traffic, like for instance, if you have a lot of unclassified traffic, it'll set an alert, and then an analyst will come in and like trigger packet capture, and you can trigger like like filtered packet capture. We say like, only give me like the unclassified traffic from this particular IP to this particular port, and then they'll go and analyze that. And I actually worked with a vendor that, without me saying anything to them, anything whatsoever, we were doing like a trial at the company I was working for. They saw a bunch of anomalous traffic, did full packet capture, analyzed it in their lab, wrote a new profile for that traffic, and pushed an update to all of their clients in the world, and then told me like, hey, we saw some weird traffic on your device, so don't worry, we took care of it. And so I didn't want that because I was trying to put anomalous traffic through their device. But that's, so they're a great company. I would definitely buy their stuff because, they're on top of their game. And so yeah. But yeah, I mean, there is some offline stuff, but I haven't really experienced it. I hear about this offline stuff where they'll like probabilistically like sample stuff. Like every now and then they'll take a connection and just record it and send it to like a backplane to do like some really detailed analysis. And then if they find anything, they'll go ahead and just block that host. But my feeling is, so in order to keep up with the traffic, you can't be capturing everything and analyzing everything, right? So if I can get you to pass through 90% of the traffic and only sample and block like 10%, then I've already won without doing anything, right? You're letting 90% of the traffic go through. So great, that's great. If people are moving to offline stuff, then I'm fine with that. Now, in terms of DDoSing the filtering hardware, I don't know about that. I wouldn't want to be involved in anything like that. That would make me sad because they're doing their best. They're just trying to do their job. I don't want to mess with them. I just want to defeat them. It's like a game of chess. It's like a friendly rivalry. What's up? Yeah, you had a question. I've been ignoring you. I'm sorry.
So, I guess when generating the model, does the program essentially have like a hard-coded list of properties it looks for, like length and height frequency, or can it adapt to different methods?
Yeah, so my general approach will work for any properties that you can have a probability distribution. So I can always add a new property. And I do, I started with the literature on this topic, right, is what I built my model from. And then I found out the literature was like vastly out of sync with reality. And so now I've updated to be based on empirical results. So the model itself has a static set of properties, but I just kind of decide on them as I go. So new versions of the models have different properties. For instance, I'm going to add this property of requiring certain byte strings instead of just forbidding certain byte strings. I'm going to add this, at this position, you must have these bytes no matter what the rest of it looks like. I'm adding that, in the next version.
But it's always possible that someone is using like a filter that screens for some property that isn't on the list.
Yeah, so the success of my system is based on the accuracy of my model. So if I don't have an accurate model, then it's not going to work very well. And so the question really is not like, will this approach work? The question is, can I make an accurate model? Do I have enough information about the filter to build a model that will work? And so in the case where I have the hardware, obviously I do, because I have like all the time I need to try all the different variations. And I have all the documentation. And in some cases, I've been able to talk to the sales engineers and ask them what their hardware did. And they told me. And, and so that was fun. That was great. So in the cases that I only have anecdotal reports, my model might not be very accurate. I think, though, that thinking that there's some kind of like a magical property that will be hard to detect that people are using it, but it will like really divide traffic well, I don't think that idea, that's an idea that people bring up to me a lot. I don't think it makes any sense. Like any property that traffic has that you can divide traffic into two categories very nicely that map to something meaningful, like the traffic you want to block and the traffic you want to pass, that's going to be an observable property that other people that look at how you've divided the traffic are going to be able to figure out what property you're using, unless you're using like some kind of like out of band sort of property, right? Like maybe you like know like the addresses of the people's IPs, and they're using like their address information to, something like that, some kind of out of band property. But if it's a property of the traffic, then you should be able to figure out what the rule is. But that's something definitely people ask me a lot. Like, what if there's some kind of other kind of classifier you haven't thought of? Yeah. Yeah. So entropy is actually a great way to do it. Entropy works. I did some tests, and like entropy is a great way to distinguish traffic. It's surprisingly effective. And so the only time that I've seen entropy actually used, not in the literature but in real hardware, is this random looking flag where they say that the traffic has like too high of entropy. But my overall approach of the reverse Huffman encoding would allow you to adjust the entropy to arbitrary levels. And that's actually why I put it in, was because when I was making this purely obfuscated random stuff, people would always say, oh, well, an entropy attack would just be so trivially defeat that. So I said, well, I'm going to show all those critics, and I'm going to have adjustable entropy. And yeah, so reverse Huffman encoding provides that. No, slides are not available. No, because, I like to keep it underground on my stuff. The video, I think, is going to be online, and that's the conference's prerogative. I said that's fine, but I got my links. Let me go back to my last slide here. These are all my bonus slides. Bam. So I got my links here. So I got I don't have my paper on there. I had it on my other slide. So anyway, I got a paper. I got a couple papers. I got my source code is all online. So and you can email me, and I'll tell you whatever you want to know about it. But yeah, I don't want to put slides up there. So we got 30 seconds. Anybody? Yeah. Mm-hmm. Yeah, that's a great question. Yeah, can I finish this question? Okay, I'm out of time, but I'll finish this question. So yeah, the Tor guys are my friends. I've known them like for a long time, since like the Free Haven days, and much respect to Tor. I will say that I disagree. I want to do different design choices than they did, and so one of the things about making an anonymity tool is that they can't know who their users are. They can't, because if they could, it just defeats the whole thing. You can start dividing people into little pockets and de-anonymizing them. And that's a choice that they have to stick with. But I think that people kind of take that and apply it to other tools where it's not really necessarily true. So I think that in my case, I don't have to be, I can know who my users are. I'm going to partner with specific people and make sure that they're using the tool in a good way. And if they're not, then I just don't have any, I don't want to spend any of my time helping bad people make the internet a worse place, right? So that sounds good. Yeah, partnering with like universities, I could do that. I mean, my general thing is to find partners that want to run this. So yeah, hit me up. I'll give you a card, and we'll see if we can start a node or something. Cool. All right, well, that's all my time. Thanks, everybody, for coming to my talk.